Igneous Rocks, Part 2, Magma Melting and Crystallization. Melting. What is melting? We start with a solid, which has a crystalline structure by definition, and if you add heat, the molecules within the crystalline structure start moving so quickly that they break away and they become a liquid. So how do you melt something? Well, the easiest way to melt something is to simply increase the heat. However, there are other ways to melt. After all, pressure holds a crystal together. If you decompress it, the crystal is capable of melting, if in fact it's warm enough to do so. There's a third way. Simply add water. Adding water decreases the temperature at which a crystal will melt. Let's look at a typical temperature-pressure curve. Here we have a graph in which the temperature increases to the right and the pressure increases as you go down into the earth. In this case, rock A is solid. It's near the surface and it's cold, where rock B is liquid, also near the surface but hot enough to melt. Whereas rocks C and D are deeper in the ground under greater pressure, so rock C is solid and D is in the process of melting. So rock A, now solid, only needs to be heated to turn into a liquid. It can stay at the surface, but if it hits high enough temperature, it's melted. However, if rock A is going down a subduction zone, it is getting heated. However, at the same time, it's increasing its pressure. So down here at C, it's still going to be a solid. On the other hand, rock C here only needs to be brought up to the surface in order to melt, as rock B is melted. It didn't need any increase in temperature, just a decrease in pressure, decompression melting. Remember, however, that water plays a part in melting. So rock E here could be melted only if there's water present, and it would be to the right of the melting point and be a liquid, or if there is no water present, it is still going to be solid. You know that melting occurs at the mid-ocean ridge. Well, why? We know that the two plates move apart. That's decompression. The asthenosphere, which is solid or almost solid, comes up to fill the gap. But as it loses pressure, it is then able to melt and fill in these cracks within the splitting ocean plates. So mid-ocean ridges are a classic example of decompression melting. So why does melting occur at an ocean-to-ocean convergent boundary or subduction zone? Well, as the plate is subducting, it is, of course, getting hotter. But that can't be enough. Otherwise, the increased temperature would melt the asthenosphere anyway, and the asthenosphere is not molten. It does start to melt, however, as these rocks get far enough down. They're carrying with them water, both within the rock and as part of the minerals. At a particular temperature, the water ends up becoming released. That released water melts the mantle and results in magma being formed, coming up and making a nice volcanic arc. So once again, this is an example of the addition of water changing the melting point of the rock. Why does melting occur along an ocean-continental convergent boundary? Well, of course, same thing. You add water, water melts the mantle. Also, the mafic magma that comes out of the mantle is going to get underneath that crust and melt it. The result will be felsic and intermediate rocks. How about at a continent collision? Do you have much melting? Not much. I mean, you used to have melting during the subduction before the collision, but that's all done and over with. Whatever melting you might have because of burial will probably just turn into felsic rocks like granite, cool underground, and never make it to the surface. So that's why you don't tend to have any volcanoes associated with a continent-to-continent convergence. How did the water get into the subduction zone in the first place? Well, it probably started back there in the ridge. The water was added between the pores in the rocks, and the minerals themselves take up the water. And later, in the subduction zone, that water is released at depth. Magma is also associated with hot spots. Rising all the way from the core mantle boundary, you have a plume of hot rock. When it gets to the bottom of the lithosphere, it's finally under so little pressure it can start to melt. And the result is magma coming up and forming ocean islands like the ones in Hawaii. But that's underneath an ocean plate. If it happens underneath a continental plate, then you have a different kind of melting going on. Sure, you can have the very basaltic magma coming up to the surface and making gigantic basalt flows. But also, that hot magma can heat and melt the continental crust. And when continental crust melts, it's very, very explosive, and you can have a caldera and, yes, indeed, a mega volcano. We've been talking about magma as if it was a single substance like water with a single melting point. But in fact, magma is much more complex than water. It might be totally melted at 1200 degrees Celsius, which would be its liquidus. However, as it cools down, it doesn't suddenly turn into rock, but some crystals form at one temperature, others continue to form at another temperature, until finally, at around 1000 degrees, all the crystals have formed and it is totally solid. So at 1000 degrees, it would have reached its solidus. Now in this example, the crystals that form at different temperatures happen to be iron oxide and apatite and these minerals. Well, we're going to deal with the most important minerals in the earth. And you know what they are, of course. They are the silicates. The order in which the silicate minerals form from cooling magma is known as the Bowen's reaction series. And that is the topic of our next podcast.